All right, good morning or afternoon, year 10. Welcome to the lesson on, you guessed it, AC generators. So keep in mind that so far we have looked at, keep in mind this is the topic called electromagnetism. And we have so far covered magnets. We looked at permanent magnets and electromagnets. And we looked at electromagnetic induction, which is also called the motor effect. And that is just when you move a wire through a magnetic field, an EMF or a voltage gets induced across the ends of the wire. And if that wire is a part of a complete circuit, then a current will flow. So anyway, we've done those two things. Now we're moving on to AC generators. And the thing about generators is that, of course, they use the generator effect. They use electromagnetic induction. Okay, so let's see. Before we get started here, we need to understand the difference between AC and DC. So alternating current and direct current. Let's start with direct current. So direct current is very simple. This is what batteries provide. If you have a battery supplying energy to whatever, the electrons in the wires will be all moving in the exact same direction. So in this case, they are all moving this way. They're all moving in one direction. They only ever move in one direction, and that's it. That's direct current. But, so if we looked at a current, remember the symbol for current is an I. The symbol for current is an I. So if we look at a current against time graph for that, you'd see that the current is just constant. It's some positive value, just meaning it's going in the same direction, and it's constant. So the current is not changing at all. Okay. However, for alternating current, so this is when you plug something into a wall socket. All the wall sockets in your house have alternating current in them. And that just means that the current, instead of going in the same direction all the time, it alternates. So it goes this way, and then it goes this way, and then it goes this way again, and then it goes this way again. And the electricity in your walls, it switches back and forth like this, from this way to this way. It does that 60 times every second. So every second, it alternates 60 times. And that's just what alternating current is. All right. So if we looked at a graph of current against time for alternating current, you'll see that it starts one way and it goes and hits a peak current, and then it goes back down, and then it hits zero for a second, and then it goes into the negatives, and then it goes back up to zero. Now you might be wondering one thing: what does it mean that this side is positive and that this side is negative? Is this side positive and this side negative? All that means is positive might just mean the current is flowing in this direction, and then negative might just mean the current is flowing in this direction. So there's nothing positive or negative about the current. It just means whether it's flowing to the right or to the left. That's all that the positive and negative means in that case. So don't let that confuse you. Okay, so that's alternating current and direct current. So moving on. So AC generators are found, of course, at generating stations. So all of these things are just electricity power generating stations. So this is obviously a hydroelectric power plant, and it just uses the energy from the water that's way up here. And when it falls down to the bottom, as this water falls from up here and falls down to the reservoir below, they just use that falling water to turn a turbine, which turns a generator to make electricity. Same thing over here. We have over here, there are wind turbines. Oops. We have wind turbines. So wind turbines just use the wind's energy to turn these turbines. The wind's energy turns these turbines, and that turns a generator. Same thing down here. Here we have tidal generators. It just uses the energy from the tides going in and out every day to spin these little turbines that turns a generator. And over here, this might be like a nuclear power station where they just basically use nuclear fuel, which just basically gets really, really hot. And they use that to boil water in a closed system. And when that water expands, it takes up a lot more volume, and they use that expansion to turn a generator, to turn a turbine, which then turns a generator. So that's just what all of that says. You can read this over in your own time. Okay, so turning motion into electricity. This is what AC generators do. They turn motion, something moving, into electricity. And they do that using what's called a rotating coil generator. So here is like the simplest version you can get of a simple rotating coil generator. And so I just want to point out a few things in this picture here. So first of all, notice that there is no battery connected anywhere. There's no battery because this is producing the electricity. It's the movement of this wire that is producing the electricity. So keep in mind, you have to have something, either wind or the expansion of water turning into gas, or maybe even just a hand crank. Something has to be turning this, okay? You have to have some input that is turning this generator. And just notice a few things. So maybe before we get to this, I'm just going to slide over to, if I can find my mouse here. Just going to, oops. Why can't I move here? What? Okay, we're just going to move over here for a quick second to this. So this is just to quickly recap the fact that generators work by electromagnetic induction. So just keep in mind, understand again what that is. So if you have this piece of wire, like we have right here. So this piece of wire, if this piece of wire gets pushed downward, if it gets pushed down in this direction, well, then this piece of wire is going to be cutting across all of these magnetic field lines, which you can see going this way. And when this wire cuts across those field lines, that's what pushes the electrons in one direction. So you have this wire being moved across, so cutting through magnetic field lines, and that basically induces an EMF, which is just a voltage. And that if this wire is a part of a complete circuit, like we have here, we have a complete circuit, then a current will flow. And so basically it's the movement of this wire cutting across these field lines. So as you move it down, it's going to cut across all these field lines, and it's going to induce a current in the wire that turns in one direction. Okay? So that's basically the base. That's how generators work. They use that principle. So now let's go back over to this AC generator. So just look what's happening over here. Let me pick another color here. Oh. Okay, so we have two parts of a wire. We have this side of the wire. Maybe I'll pick a different, more visible color. Maybe this one. I'll go a little thicker. So we have this side of the wire here. Why that didn't work. So we have this side of the wire over here, which is moving downward. So this side of the wire is moving down. And then we have on the other side, we have this side of the wire, which is moving in the upward direction because this thing is spinning. Okay? So one thing I want you to notice is that, okay, we're going to just look only, let me just change that color. We're going to look only at this side of the wire for a second, okay? So this side of the wire, we said, is moving downward at the moment. So you don't need to know the right-hand grip rule for the right-hand palm rule for generators, only for motors. So last week when you learned that, you won't even need it. But let's just say, using the right-hand palm rule, if we point our fingers from north to south, and then we point our thumb downward, you'll see, so point your fingers from north to south, point your thumb down, you'll see that the palm of your hand ends up pointing in this direction that current is flowing. So in this side of the wire, current is flowing in this direction. Now, just think for a second, what will happen when this piece of wire rotates? Because remember, this thing is spinning right now. So 180 degrees later, when this part of the wire moves over to this side, let's think about what happens. Now this wire has moved over to this side. So now, instead of moving down, now all of a sudden, it's now moving upwards. So just think, over here we said the current was going this way in this piece of wire. But now, 180 degrees later, when this wire flips over and moves over to this side, now instead of moving down, it's moving up. And so let's do our right-hand palm rule again, which again, you don't really have to know, but it just helps in this instance to describe what's happening, why this is alternating current. So if you point your fingers from north to south again, but now if you point the palm of your hand up, you'll find, or sorry, if you point your thumb up, so your fingers north to south, your thumb points up, the palm of your hand is now pointing this way. So just notice that when the same piece of wire was over here, the current was going this way in it. But 180 degrees later, the current is going the other way in it. That is precisely why AC generators produce AC current, alternating current, because it's going one direction, and then a split second later, it's going the other direction. It's alternating directions every half turn. Okay, I hope that makes a bit of sense. That is why generators produce alternating current. So, just keep in mind that electromagnetic induction, which is how generators work, they require three important things. They require a magnet, we see the magnets here, a coil of wire, and some rotational energy. There has to be something that is rotating this. Don't forget that. And then it says down here, continuous AC current is produced that way. And remember, it's alternating because when that side of the wire was on this side, the current in it was going this way. When it moved to the other side, the current was going in the opposite direction in it. That's why the current is continuously alternating. It's continuous AC current. And this is how all the electricity used in your home is produced, only on a much bigger scale than what we see there. Okay, so again, so here, this is just a reminder that you have to have an energy input. In this case, in this little picture, you would have to have your hand that's turning this around. This is a hand crank like the one that we have at school. So just remember, generators require some energy input, and it turns that energy into electrical energy around the circuit. Okay, so now you might have noticed on this picture up here that there are these things that I just kind of have ignored so far. We have these slip rings and we have these brushes. So I'm talking about these two things. This is a slip ring, this is a slip ring, and then we have these two things right here. That's one, that's a brush, and there is the other brush right there. And you'll see these brushes, all they do is maintain electrical contact with these slip rings. I'll explain this with a different picture right now. So let's go back down there. So it says, what are slip rings and brushes? What do they do? So let's look at this picture. So here again, we see a generator, a simple AC generator, and we see the same thing. So here we have these two slip rings. Here's a slip ring, here's a slip ring, and then we also have these brushes. Here's one brush, here's the other brush. And just notice, all that these things do is it allows this coil right here to keep rotating around and around and around and around and around and around. It's just rotating constantly around in the same direction. It just keeps rotating. What these do, what these slip rings and these brushes do, it just allows this coil to spin and maintain electrical contact to the external circuit. Basically, it just allows this to spin without wires getting tangled up. Because as this coil of wire is spinning around and around and around, these slip rings are also spinning around and around and around. And this slip ring is spinning around and around and around. And this brush, so these brushes right here All they do is keep in contact right here. They're just maintaining, all these brushes do is maintain contact with that. It just allows this thing to spin around and around and around, all while touching it. So it's just touching it, and electricity is still conducting through here all the time. The electricity is still conducting through there. It just allows these things to spin while maintaining electrical contact right here and right here. That's all they do. So I'll show you over here. So basically, slip rings and brushes allow the coil to spin without this happening. Otherwise, you would just get a tangled mess of wires just like this. And in no time, within a second or two, those wires would probably just end up breaking. So that's all those slip rings and brushes do. They just allow electrical contact while that ring, while the thing is spinning, while the coil is spinning. And you'll see, if slip rings and brushes were not used, the wires would get tangled up. So the two ends of the coil are attached to slip rings. The brushes just allow contact to be made while the slip rings spin. It just allows the coil to spin and electrical contact to be maintained the whole time. Okay, so now let's say we have our simple AC generator and we want to generate the biggest current possible. How can we maximize the size of our current? Well, there's a few things you can do. Take a guess. Well, you can think, number one, you'd probably want to have this spinning as fast as it can. So here we go. What you can do is you can rotate the coil faster. You can just rotate the coil as fast as you can. That's going to induce a greater current. You can use a stronger magnet. So if it has to happen, if the electricity is induced by the wire cutting across the magnetic field lines, well, the stronger the magnet, the more the field lines there are, the stronger or the greater the current you're going to get. So if you're trying to maximize the current, you want to rotate that coil as fast as you can. You want to have the strongest magnet you can find. And instead of just having one turn of coil, you'd want to have many, many turns of coil. So we can see over here in this picture, all we can really see is one turn of coil right here. But really, a generator would be made up of hundreds and hundreds of turns of wire. Because keep in mind, every time you double the number of turns of wire, you're doubling the induced current. Simple as that. So there would be hundreds and hundreds, if not thousands of turns of wire here as this thing spins around. It wouldn't just be one single coil of wire. It'd be hundreds, if not into the thousands. And then finally, one last thing you could do is place an iron core in the middle of this coil of wire. So you just have a piece of iron in the middle of it. And all that piece of iron does in the middle of this wire is just strengthens the magnetic field. That's it. So basically, that's almost the same as the first one, or sorry, the second one. Use a stronger magnet. So this one, by adding an iron core inside of this, it just strengthens the magnetic field from this external magnet. So those two are kind of similar. Use a stronger magnet and the iron core. They both have the effect of increasing the strength of the magnetic field in between those two poles of the magnet. So just remember, you can spin it faster, use more coils of wire, or a stronger magnet. Don't worry too much about the iron core. It's very unlikely to come up on a test. Okay, so you'll see here is a link to a nice little animation, which I cannot currently click on. Let's see. Here we go. So you'll see this is just a beautiful little animation. Always translate German, sure. Always translate it. Okay, so you can see here, here's a very simple generator. And what I like is this is showing at the top here, you can see the graph. So you can see this blue dot moving along the graph as this thing is spinning. And just notice over here, it's showing the voltmeter. And just notice it's going one way, positive, and then it's going the other way, negative. And all that means is the current is flowing one way, then it's flowing the other way. Then it's flowing one way, then it's flowing the other way. And do keep in mind again that all of this is happening because this side of the wire and this side of the wire are constantly cutting these magnetic field lines which pass this way. It's that wire, the coil of wire cutting across these field lines that is inducing the EMF, which induces a current. That's really it. So back to our presentation. Okay, I'm going to suggest, so at the bottom of this presentation, you'll see this video, and it really does a super duper fantastic job of explaining with a nice animation to go with it how AC generators work. And now that you already have a solid background, take a look at that video. It should really help your understanding a lot. I do want to point out one thing is here they'll talk about Fleming's right-hand rule for determining the direction. So keep in mind, in coordinated science, you don't even need to know how to figure out the direction of the current. That's only for separate science. So last week when I went over that, I shouldn't have. So don't worry about it if you didn't get it. If you did get it, great. But what we use the right hand, I call it the right hand palm rule. And that's where the palm of your hand points in the direction that the current would flow. Here, they use Fleming's right hand rule. You'll see, though, that it gives you the same answer as the right hand palm rule, only this one is much, much easier. Trust me, you'll see the difference. So in this video, if they explain it using Fleming's right hand rule, just pause the video and try our right hand palm rule and see if that gives you the same answer, because it should, and you'll see that it's a lot easier. Okay, so I believe that is the end of this presentation, and it is. So go through this presentation yourself, look at that video, and then try the multiple choice questions that I have assigned to you. They're pretty straightforward, and they're self-marking, and whether you get the question right or wrong, it will give you a detailed explanation of the concept in the question. I spent a lot of time setting up those Google Forms with the multi-choice quizzes, so please take your time going through them and review your answers with what I wrote, whether you get it right or wrong, okay? So good luck with all that, and we'll see you during our next video presentation. If you have any questions about anything, just send me an email or drop a message on the shared document for questions, whichever you prefer. Okay, so good luck with that, and we will see you shortly. Okay, where has this gone? How do I close this? There we go. Okay, good luck, guys. If you have any questions, just call me or send me an email.